So most of us have heard of climate change, and we know the idea that if we dump more greenhouse gases into the atmosphere, the Earth should get warmer due to something called the greenhouse effect. So what we're going to try to do today is actually come up with empirical laws that govern that. We're going to try to derive from physics how much the Earth should warm given certain conditions. And in fact show that greenhouse gases even cause warming at all. So in order to do that, we're going to approximate the Earth as a blackbody. A blackbody is a material or a substance or some object that absorbs 100% of the light that is incident upon it and re-emits 100% of that light back. So, of course, the Earth is not actually a blackbody. It reflects light. We can see that when we look down and the grass is green. But we're going to find that actually that approximation to the first order is very good. And in physics, physics is all about approximation. So it's going to be a good approximation, and particularly because we're actually going to try to account for some of the light that's reflected from the Earth, even though it varies a lot depending on whether you're in a desert or a forest or an ocean or a city, right? So you're going to get a lot of different reflectivities, but we're going to try to account for some of that, average it out. So here we go. So I'm going to introduce you first to the Stefan Boltzmann Law. So the Stefan Boltzmann Law tells you about the power per square meter that is radiated from an object that is a blackbody. So that power per square meter term is I, for another word called the insolation, most likely. So insolation is spelled like this, because a lot of times we use this when we're talking about the sun and the amount of power that the sun radiates. So insolation I is equal to the Stefan Boltzmann constant, lowercase sigma, times temperature to the fourth, where the temperature is the temperature of the blackbody. So the Stefan Boltzmann constant is 5.67 times 10 to the negative 8th, and you should actually be able to figure out the units, right? If this is power over area, then, and this is temperature to the fourth, then this should be power over area times temperature to the fourth, which indeed it is. So we're all set. So we're going to use this to try to set up a toy model of the Earth and see what happens. So what we want to do first is try to set up a baseline. So we want to know, before we start dumping greenhouse gases into the atmosphere, what should the temperature of the Earth look like? So let's assume that there is only O2, oxygen, and nitrogen in the atmosphere. And we're also going to assume that there is no atmospheric absorption of infrared radiation, heat. So no atmospheric absorption of IR radiation. So what we want to know then is how much of this power per square meter is the Earth going to actually feel? How much of that is going to contribute to the temperature of the Earth? So it turns out that the sun gives off, this little circle with a dot in it is usually written for the sun. So this insolation, power per square meter coming off of the sun, is equal to 1,370 watts per square meter. Okay? So this is what's coming off the sun in total. But we want to know how much does the surface of the Earth actually feel. So in order to figure that out, well, at any given moment, if the sun is here and the Earth is in front of it, only the fraction of the Earth's area that's facing the sun is actually going to feel any of that insolation, right? So that's going to be, we're going to cut it up a little bit. So the I that we're going to be interested in is going to be equal to this from the sun, and we're going to have to subtract from that, sorry, not yet. What we're going to have to do is we're going to have to multiply that, right, by the amount of the Earth that's facing it. And that is going to be the area that's facing the sun divided by the total surface area, 4 pi r squared, where this is the radius of the Earth. Good. And if we do this out, plugging in, this is 1370 watts per square meter, we're going to get 343 watts per square meter. Since really all we're doing is dividing this by 4, right? Pi's go away, the r's go away. So we only have 1 over 4. So that's how much radiation the Earth is actually feeling. So from here, we want to factor in a little bit the fact that the Earth is actually reflective, right? So let's say the reflectivity, there's a word for this, it's called the albedo, and it's represented by alpha. So we're going to call this albedo. And we're going to set the Earth's, in this model toy Earth, at 0.16. So it reflects 16% of the light that's in it. So, doing that, what we want then is we're going to have to take the total amount of power per area that the Earth feels, which is 343, and subtract from that all the light that's being reflected away. Right? So, what we're going to have is I naught, or so the total I'll write I total is equal to this I minus alpha times I. Right, 16% is reflected, and the total amount that the Earth is going to feel is going to be I times 1 minus alpha. So this is going to be equal to then 343, the units, 343 watts per square meter times 0.84. And if we calculate that, this is equal to 288.12 watts per meter squared. Okay? So this is how much the Earth is actually feeling that's going to contribute to the Earth heating up and getting a temperature. Right? So from here, we only have one more step. So to calculate temperature, we're going to go back to our Stefan Boltzmann Law. And the Stefan Boltzmann Law says that our temperature equation, right? So we have I is equal to the Stefan Boltzmann's constant times temperature of the surface of the Earth to the 4th power. So going from here, we can solve for Ts. So the temperature of the surface should be the 4th root of I over sigma. And when we plug in 288, and we plug in our value for the Stefan Boltzmann constant, we get the temperature of the Earth is equal to 267 Kelvin, which, for reference, is equal to negative 6 degrees Celsius and 21.2 degrees Fahrenheit. So, we're saying this is the temperature of the Earth in a situation where it really has no atmosphere at all. And it has an albedo of 0.16. So we're actually, even before we start putting in atmosphere or gases or anything like that, we're really not that far off. The actual temperature of the Earth, I will write up, actual, is, 287 Kelvin. So we're only off by 20 Kelvin. And again, to give you an idea of what that is, that's 13 degrees Celsius and 56 degrees Fahrenheit. So already, we can really see the power of this physics. The fact that it's able to give us an answer that's actually close to what we really see. So, moving on, the next step that we want to do is we want to look at the greenhouse effect. So, we're going to introduce some atmosphere. So, now what we want to do is include infrared absorption of radiation by greenhouse gases. So I'm going to say that this is the surface of the Earth, and we now have an atmosphere. That's that. So the surface of the Earth is going to have a temperature, and I'm going to call it T sub S. And the atmosphere is also going to have a temperature, and I'm going to call that T sub A. And what we're interested in is obviously the temperature of the surface of the Earth. And there's an important condition that allows us to make these calculations. So what happens is if I just take a rock, right, which the Earth essentially is, you take a rock and then you stick it near a sun, right, it's going to heat up and it's going to be increasing its temperature, right? So we want to look at the system after it hits equilibrium. And there's a very special kind of equilibrium called radiative equilibrium, where the amount of power coming in to the Earth, the amount of power being absorbed by the Earth, is equal to the amount of power being radiated back out by the Earth. So what's happened is everything's kind of settled down. This is when we're going to be looking at this and trying to find the temperature. So we have our, in this situation also I want to change it a little bit, and we're going to set the albedo to be 0.3. So we're actually going to increase the amount of light that's being reflected by the Earth and see what happens, in addition to atmosphere. This is actually closer to the Earth's real albedo if you average it out over the whole planet, the planetary albedo. It's about 0.3, 0.35, somewhere around there. So we're going to say we have radiation coming in from the sun, right? And this radiation coming in is equal to 0.7 I. So 0.7, because again, the 0.7 comes from the 1 minus alpha times I, which we saw over here, 1 minus alpha I. So we're multiplying 343 times 0.7. And that's the amount of radiation per square meter that's coming in at the Earth. So the Earth is going to absorb that, but then it's going to radiate it back out. Right? Up and out. And this atmosphere is going to absorb that radiation. Right? And that, after the atmosphere absorbs it, it also radiates it back out, because we're modeling everything as a blackbody. So this radiates it back out, down, and up. Important thing here to note is that each of these arrows does not represent half of the radiation of this. Black bodies radiate uniformly in all directions. So this is equal to this is equal to this. Because again, power in equals power out. So, radiative equilibrium, we can set up our equations. And what we're going to have is we want to look first at the temperature of the atmosphere. So, that's going to be sigma times temperature of the atmosphere to the 4th power. And we want to know, well, what can we set that equal to? What kinds of, this is going to be the power coming out. So maybe I should have switched these. Power out was power in. Same thing. I'm just going to write out on this side. So it's radiating out sigma TA to the 4th, right? That's what a black body radiates. So that's going to be equal to the power coming in. And the only power coming in here is 0.7 I. Okay? And then we also want to find the temperature of the surface of the Earth. So we have sigma temperature of the surface to the 4th, and that's the amount that it's radiating, right? Radiating that out. And what is it feeling? Well, it's feeling this contribution, which is 0.7 I, but it's also feeling the re-radiation coming from the atmosphere, right? So we're going to add to that sigma TA to the 4th. Now you might ask at this point, well, if it's absorbing this from the atmosphere, isn't it going to radiate back out again, right? And then it can hit this, and then this will re-radiate out again, and it will go on forever. We're only going to be looking at first-order effects because we want to preserve the integrity of the model, and what happens is, in real life, you actually get some degradation of the radiation, right? So eventually it's going to taper off to 0. So we're just going to stick with the first-order terms, and that should give us a good approximation. So, looking at this, we can say that we know the power in is equal to the power out, right? And every arrow on here is really the same, which means we can substitute this 0.7 I for a sigma TA to the 4th. So doing that, well, it actually makes more sense to substitute this for a 0.7 I, right? Because we know what 0.7 I is, because I is equal to 343. So why don't we do that instead, and we'll say that sigma TS to the 4th is equal to 2 times 0.7 I. And now you can go through, you can just divide both sides by sigma, you can take the 4th root of everything, and you'll find that the temperature of the atmosphere, because we can get that too, just divide and take the 4th root, is about equal to 255 Kelvin. And the temperature of the surface is about equal to the fourth root of 2 times the temperature of the atmosphere. So maybe in my notes, I think I did substitute back in for TA. And this is equal to, let's see, 303 Kelvin. So the thing to note here that is very significant is the original temperature of the Earth, when we had no gas and no absorption and none of that stuff going on, was 267 degrees Kelvin. We put in one layer of atmosphere, and the temperature jumps 40 degrees. This is a non-trivial effect. This is big. And what we even did was we even increased the reflectivity. So if we decrease this back to 0.16, which is kind of an arbitrary value I chose over here, that's going to increase the temperature even more. So the greenhouse effect is a formidable effect when we're looking at temperature increases on planets. So now let's again see what happens if we put more gases into our atmosphere. So I'm going to erase this, and now what we're going to do is we're going to set up a toy model again that has 2 layers of atmosphere instead of just 1. And we're going to do that to try to represent the idea of introducing more greenhouse gases into the atmosphere and looking at how that further alters our temperature. So I'll also keep a little running tally here. So 303 over here, if we had no atmosphere, we had a temperature of 267 Kelvin. Okay? So let's go ahead and do this. So now we're going to say we have 2 layers. So this is a 2-layer model. So we're going to put one here, and the surface. So we again have our incoming radiation. Maybe I should make this a little bit bigger. So this is the temperature of the surface. I'm going to call this TS. This is going to be T1, and this is going to be T2. So we have our incoming radiation. We're still assuming, notice, we're still assuming that the atmosphere is completely transparent to incoming radiation, and it only blocks stuff on the way out. And we're going to modify that in a little bit and try to get it more accurate. But for now, that's the assumption we're going to make. So here we have the incident radiation I, and then this is going to radiate back out. And what's going to happen is, again, it's going to hit this atmosphere, and this atmosphere is going to absorb the radiation here and re-emit it. Then this atmosphere is going to get this radiation, absorb it, and re-emit it. So now our equations are a little bit more complicated than they were last time. So looking at the first atmosphere here, T1, we're going to set up our equations for radiative equilibrium. And we have sigma T1 to the 4th is equal to the time averaged incident radiation. All right, incident here. So if you're not familiar with this notation, this is just time average. I could have used it over there too. I did not. But this is really just the amount of radiation coming in. I'll just get rid of it. We can just say it's I. The reason for that, right, is because you're going to have a lot less radiation at night than you are during the daytime, for example. So we average it over all time to get a better approximation. So I'll just say the incident radiation coming in, and remember that this is going to be equal to 1 minus the albedo times I. The original amount that the Earth would have felt had it not reflected some stuff. And this is because this only gets one arrow, right? It only gets one input of radiation coming in. For the second atmosphere we see gets this initial contribution, then it also gets a contribution from T1. So to account for both of those, we're going to say we have I coming from the surface, but we also have sigma T1 to the 4th coming from the upper atmosphere. And remember that all this stuff is equal, which means this is equal to this, and we can say that we have 2 sigma T1 to the 4th. And then finally, we can do the temperature of the surface, and this is going to be equal to the incoming radiation plus the radiation from the second atmosphere, right? So I plus sigma T2 to the fourth. And in the interest of minimizing our variables, we know that sigma T squared, 2 to the fourth is equal to 2 sigma T1 to the fourth. So we can make that replacement, and remember that this is equal to everything else, which means this is also equal to this. So we can say this is equal to 3 sigma T1 to the fourth. Okay? So, coming from here, you're just going to solve this, and at this point it's trivial. You'll just divide by your 3 sigma here, and you'll set this up with the other equations, and you can substitute if you need to, because we have a few equations with a few different unknowns. But we can start by solving this one. We can take this, divide by sigma, fourth root it, we get T1. So now we have T1, we can plug it in here, divide by sigma, fourth root, and we get Ts. So, if you go through and do all that, which I'm not going to do because it uses up time, we get that the temperature of the surface is about equal to the fourth root of 3 times 255 Kelvin. And this is equal to right around 336 Kelvin. So again, we went from 267 Kelvin to 303 Kelvin, and now to 336 Kelvin. So adding more gas to the atmosphere will increase the temperature of the Earth. This is a relatively conclusive result based on the physics here. So we know that is going to happen. However, we still know we're making some assumptions. We're pretending that the atmosphere doesn't reflect anything on the way in. So let's try to make this a little bit more accurate, a little bit more realistic. And we're going to do that by now saying that the atmosphere layers do in fact reflect some of the incoming infrared radiation. And doing that will give us a more accurate result. I'm also going to erase this. Okay. So we're going to set up our toy model. So we're going to have our upper atmosphere, our lower atmosphere, our surface, and our 3 temperatures. So we're going to have T surface, T2, and T1. Fill these in. Now what we're going to have our incoming radiation. Okay? And then we're going to bounce this out. And what we're going to say this time is that this actually bounces all the way through. So some frequencies, what we're doing here is we're saying that some frequencies are absorbed by the atmosphere, and some frequencies are not absorbed by the atmosphere. So this lets some go through, and some of it is going to come out here and be absorbed by the second layer of the atmosphere here. Which this will then say, okay, well I'm re-emitting here, I'm going to re-emit here, but I'm also going to re-emit some right through the top layer. And the top layer then says, okay, well I'm going to have some come in here, some go out there, and we're going to shoot some all the way down to the surface. So at this point the diagram's pretty messy, pretty much a mess. So we're not going to actually really go through all of this. What I'm going to do is I'm going to use the notation that tau sub I, I'm going to say is equal to sigma T sub I to the fourth. That way it's easier and quicker to write out the equations. So our equilibrium equations here, if we set this up and look at all the arrows, and you can do this yourself if you like, is T2, tau 2, plus 1/2 tau 1 plus 1/2 tau s is equal to I. Our second equation is that I plus tau 2 is equal to tau 1 plus 1/2 tau surface, and I plus 1/2 tau 2 plus tau 1 equals tau surface. Going through all of this, we can see that tau 1 is equal to 8/21 I, tau 2 is equal to 2 over 21I, and temperature of the surface, tau surface, is 30 over 21I, and this gives you a temperature of 291 Kelvin. So, again, we increase the temperature by creating a more realistic model, and furthermore, this temperature here, 291 Kelvin, is very close to the actual temperature of the Earth, which the average temperature of the Earth, actually, if you remember, is 287 Kelvin. So we are off by 4 degrees Kelvin. That's how powerful and solid this physics really is. And this is where we can kind of draw the line for trying to make our models more and more realistic. At this point, I feel like we've gotten the point across that dumping more greenhouse gas in the atmosphere actually does increase the temperature. And furthermore, when you account for the fact that some frequencies escape, some don't, etc., that attributes to more warming. And third, that this physics works. It is a pretty powerful tool in order to analyze a system as vast and chaotic as the Earth is. So, from here we're going to kind of switch gears a little bit, and I'm going to erase everything. And we're going to talk a little bit about radiative forcing. And we're going to use a little bit about what we don't. Okay. So, there's a quantity called radiative forcing. I guess I should erase that. I'm kind of done with stuff for now. Radiative forcing. So, radiative forcing is the difference in energy that is received by the Earth versus the energy that's radiated back, right? The Earth is not actually a perfect blackbody. So to get a better idea, we're going to introduce this concept of radiative forcing. So it is the difference in energy received by Earth versus radiated back. So, radiative forcing is a measure that allows us to relate to temperature change based on how much radiation we're getting. Radiative forcing is actually proportional to the logarithm. It grows logarithmically. So there's some constant, and then log of the mass of CO2 in the atmosphere over, we call it m star, which is going to be our kind of base mass in pre-industrial levels. So we have this relation here, and it also can tell us what happens if we double the CO2 in the atmosphere. And once we get the radiative forcing, I'm going to introduce you to a relation that from here we can get temperature. So I'm going to call, if we double the atmosphere, the CO2 in the atmosphere, we're going to call that F2x, the radiative forcing that results from doubling the CO2 in the atmosphere. This is going to be equal to, I should tell you the constant, because otherwise we can't actually calculate anything. The constant is just a measured thing. It's 3.7 watts per square meter. And this radiative forcing is equal to 3.27 watts per square meter. And this gives you, in accordance with a relation I'm going to introduce to you, a temperature change of 1.2 degrees Celsius. So, that relation that I introduced to you is, or I have yet to introduce you, that the change in temperature, this is, I'm going to put a 0 here and not, I'll tell you why in a second, is equal to negative radiative forcing over another constant called lambda. So, this I'm going to call our uniform temperature. And what this is we're assuming, so lambda is generally we're going to use as a feedback parameter. So we know that what happens is, if we heat up the Earth, then ice melts, right? And if ice melts, then there's going to be less reflectivity. And if there's less reflectivity, it's going to heat up more, which means more ice will melt. And there'll be even less reflectivity, and so on and so forth. So we're going to represent those feedbacks by quantities that we're going to call lambda. So this uniform temperature is kind of the base feedback. We're assuming that if we increase forcing, nothing actually changes, except the temperature increases. So this can tell us that if we increase radiative forcing, how much of a temperature increase do we get purely as a result of that additional radiation coming in and not accounting for any feedbacks. Okay? So this is just to set up kind of a baseline from which we can build. We're not going to actually try to model this. So this is what can give us that. So what this also tells us is what happens. Oh, I should tell you what lambda is, huh? This is lambda naught, our zeroth feedback effect. Lambda naught, where's the value? Lambda naught is equal to negative 3.2 watts per square meter degrees Celsius. So that's our lambda. So what this can tell us is if we increase the amount of solar radiation hitting the Earth, being absorbed by the Earth, by 1 watt per square meter, what will happen? If we do that, we can just plug this in, and we can say, okay, so the change in temperature, keeping everything constant except for the temperature itself, as a result of one increase in 1 watt per square meter, divided by our kind of zeroth feedback, which is negative 3.2 watts per square meter degrees Celsius, is equal to 0.3 degrees Celsius. So for every additional watt per square meter of radiation that's going to hit the Earth, we're going to have an increase in temperature of 0.3 degrees Celsius. That might not sound like much, but when you think about that, this is from 1, well, if you have 2, that's double the amount. If you have 3, you're tripling the amount. So this is not something to take lightly. So from here, let's look at some common feedbacks. Let's just talk about them. So, water vapor in the atmosphere, right? Water vapor in the atmosphere is one possible feedback. If we increase the temperature, the amount of water evaporating is going to increase, which means the amount of vapor in the atmosphere is also going to go up. Water is actually a greenhouse gas. Water, if the amount of water in the air goes up, then the radiative forcing goes up. And if radiative forcing goes up, temperature also goes up. Additionally, ice albedo. So if temperature goes up, we talked a little bit about this, ice goes down, which means the amount of reflectivity the Earth has goes down. And if reflectivity goes down, we again get more radiative forcing, which means we get a higher temperature. But there's also the opposite. You can also have negative feedbacks. So clouds, for example. Clouds are one of the most difficult things for climate scientists to really model because they can contribute to both positive and negative forcing. They can cool the Earth, they can cause negative forcing, which means the temperature has a... Notice that, again, this is a negative constant here, and we have a negative number. So if we get negative forcing, we get a negative times a negative, which is positive, divided by a negative, which is a negative. So if you have negative forcing, your temperature actually will decrease. So it's also possible to cool the Earth down by decreasing the amount of, the difference between energy received by the Earth and radiated back. So these are all possible feedbacks. So what we want to do is say, well, let's suppose that there's some feedback with the parameter that we're going to call lambda. I kind of hinted at, foreshadowed at that. So that a change in the surface temperatures gives rise to a feedback which produces more forcing. What I mean by that is, let's say we have, something that has a feedback parameter of lambda. And this forcing, the forcing as a result of that, I'm going to call it, for the first forcing 1, is equal to lambda times our change in temperature, 0, right? So this here gives rise to an additional temperature increase. Because remember that there's feedback, right? If you increase forcing, you increase temperature, which increases forcing. So we're going to say that additional temperature, we're going to call it T1, our first feedback. And this is equal to negative F1 divided by lambda, which lambda here, lambda none. Good. And this gives rise to F2, right, which is equal to lambda times the change in temperature from 1, and so, oh, I had it down there, subscript, from 1, and so on and so forth, and so on. So what we want to do is, depending on what you're interested in, we're going to have a math interlude. What I mean by that is I'm about to do lots of math. Or math that is not as trivial as the math that we've been doing. If you don't want to see it, skip ahead in the video. If you do want to see it, stick around. So, here's what we're going to say. We're going to say that we're interested in some feedback, right? And we know it's going to keep on going forever. So we want to know what is the total contribution of that feedback. So let's say we have a change in temperature of step K, right? We've been increasing 0 to 1, then 2, and 3, and so on. And this is going to be equal to negative 1 over lambda naught times the kth forcing. Okay? So here, we're going to just make a substitution. We're going to say negative lambda over lambda naught times change in temperature K minus 1. Working our way backwards. And what we're going to do is this system is essentially we're iterating by reducing K until K minus 1 equals 0. And when we do that, when we go all the way down, what does it give us? Well, it gives us that the change in temperature for K is equal to, and so we have this, right? And we can then replace this with another negative lambda over lambda naught times delta t k minus 2. Replace this with negative lambda over lambda naught times delta t k minus 3. And we keep doing that, and these lambda over lambda naughts keep multiplying together. And eventually, we get negative lambda over lambda naught to the kth power, and that's not an index, to the kth power, times our original temperature change, 0. So, if we add up all this stuff, the total change in temperature is going to be equal to delta t 0 plus delta t 1 plus delta t 2 plus so on and so on and so on and so on. Right? So the total temperature change from all of the temperature changes that cause are results of the feedback. When we add all those up, we can write that as the sum from k equals 0 to infinity of change in temperature sub k, and then that we can set equal to, we can again substitute in, so this is the sum from k equals 0 to infinity of negative lambda over lambda naught to the kth power times delta t 0. Right, that's what we said we solved for tk. This gave us this, and that's what we just put in. So doing this, we have our series, and this, again, you can review math as to how I make this next step, but this gives us 1 over 1 plus lambda over lambda naught times delta t 0. And then we can substitute in for delta t 0, and this we have negative f divided by lambda naught plus lambda. Hooray! So from here, what does this tell us? This tells us that it gives us lambda naught plus lambda times our change in temperature is equal to negative forcing. Sorry, negative, yeah, good. So this is essentially the same arrangement as our original equation here, but now we just add in this parameter here. So it kind of seems intuitive that if you have multiple feedbacks, you're going to just add them in, right? But it's nice that we proved it. So now what happens if we have more than one feedback, right? We talked about water vapor, we talked about ice, we talked about all these different things. So if we combine all of the feedbacks together, I'm not going to prove that. I'm just going to tell you that you can indeed continue to add it in. So, if you have multiple feedbacks, it gives you lambda naught, which is the original baseline thing, plus lambda 1, plus lambda 2, plus lambda n if you have n feedbacks, times delta t is equal to negative n. Good. So what this does is it tells you that these feedback effects amplify the warming of the Earth, right? Additional feedbacks will amplify it. And the amount by which you will amplify it we're just going to call it F, the warming factor. So it's going to amplify it by lambda naught over lambda naught plus 1. Which, we got from, we had 1 over 1 minus lambda over lambda naught. And this gives us that the total change in temperature is equal to F times the change in temperature, uniform temperature, which is equal to our climate sensitivity factor, is what I'm going to call that, times the force. So the climate sensitivity factor essentially tells you how sensitive is your climate to these types of feedbacks. And what this is equal to, right? Climate sensitivity is equal to negative F over lambda naught, which is equal to negative 1 over lambda naught plus lambda. So, now that we have this framework, which is kind of messy, but that's okay. Now that we have this framework, we can apply this to the Earth. And unfortunately, this is kind of where the extent of our modeling kind of reaches its limit. So this is where you have to go out and make some measurements. And doing that, the IPCC, the International Panel on Climate Change, has taken some measurements for us and has estimated that, combining all the feedbacks that the Earth experiences, the climate sensitivity factor is about equal to 0.83 degrees Celsius per watt per square meter. So, that gives us our climate sensitivity parameter for Earth. And now what we can say is that, in fact, originally we said warming by 1 degree will give us 0.3 degrees Celsius temperature increase. Accounting for all the factors that actually changed, because remember back then we said nothing changed, we see that this actually gives us a change of 0.83 degrees Celsius, which is more than twice the size of the original estimation. So this is a little bit bad. And what we can do from here is we can say, well, what will happen? Let's estimate the change in temperature using our new feedback information if we double CO2. And we're going to again say change in temperature for 2x, doubling CO2, is proportional to our new climate sensitivity parameter times radiative force from 2x, which I had erased but we had up. And this gives us 3.2 degrees Celsius plus or minus 0.7 degrees Celsius. So if you double the CO2 in the Earth's atmosphere, the temperature will increase by anywhere from 2.5 degrees Celsius to 3.9 degrees Celsius. And to give you an idea, I had this somewhere, to give you an idea of what, how fast we're growing, pre-industrially, the amount of CO2 is measured in parts per million. So if you grab a if you grab a little chunk of air and you measure how many molecules of CO2 there are per million, that's how CO2 is measured. So pre-industrial, we had 280 parts per million. Today, we have 393.31 parts per million. I took this measurement today, which was October 29th, I think. So, we've increased a lot. We're well on our way to doubling. And this is what is scary, is we do not want an increase of up to 4 degrees Celsius. That would be bad. And yet that's the path we're going on. This means that we've been increasing at about 2.8 degrees Celsius per year. Oh, sorry, 2.8, not degrees Celsius, that would be catastrophic. 2.8 parts per million per year. And obviously there are different policies in place to try to slow it down or stop it, but there are a lot of different variables that come into play politically, which make that very, very difficult. So at this point it might be interesting to ask, well, we know the Earth is warming up. How fast is it warming up? How much do we have to be worried? And we can actually use physics to calculate that. So we're going to try to calculate the time scale of the warming. So I want to know over what time period, and again, this is going to be rough. It's going to be order of magnitude, tens of years, hundreds of years, thousands of years, millions of years. How long is it going to take for the Earth to warm up? So we're going to ask that kind of indirectly by asking how long does it take to actually warm the mixed ocean layer to shift to equilibrium longer. So we want to know how long does it take to warm up the oceans, because that's really the Earth's temperature. If you've ever noticed, in the winter, oceans tend to be warmer than their land surrounding them, and in the winter, that's what I just said. In the summer, oceans are cooler than the land surrounding them, and that's because of the heat capacity of water and the fact that it takes a while to heat it up and cool it down. It holds on to heat better, or resists heat better, which is what happens. So we're interested in changing the temperature of the water, which will really result in permanent shifts in the Earth. So we know from previous calculations that the forcing as a result of doubling the CO2 in the atmosphere is equal to 3.7 watts per square meter. The volume of the Earth's oceans, well, the volume is going to be the surface area of the ocean, which is about 350 megakilometers squared, times, let's say the average depth of the ocean is 200 meters. And this gives us about 7 times 10 to the 16th cubic meters of ocean, which we can calculate the mass of that because we know the density of water. So mass, we know mass is equal to density times volume. And we get the mass of the Earth's oceans are 7 times 10 to the 19th kilograms. So we want to know how much energy does it take to get such a temperature increase. So we're going to use our heat capacity equation, which is Q equals mCp delta T. And let's see, so the heat capacity, we're going to have 4.186 kilojoules per kilogram Kelvin is our heat capacity, times the mass we just did was 7 times 10 to the 19th kilograms, times a temperature increase of 3.2 Kelvin. And that is from the same thing, right? Because Celsius and Kelvin have the same difference in scale. So to achieve a warming of 3.2 Celsius is the same as to achieve a warming of 3.2 Kelvin. 3.2 Kelvin, and this gives us, we need 10 to the 24th joules. So remember, joules is the unit of energy. It requires 10 to the 24th joules of energy to heat up the Earth's oceans. 3.2 degrees. That's a decent amount of energy. So now we get to time. So how fast is this happening? So the rate of warming, I'm going to call R. R. And R is going to be equal to the radiative forcing from doubling, so 3.7 watts per meter squared times the surface area of the Earth. And the surface area of the Earth is about 500 megakilometers squared. So here we're using the entire surface area of the Earth because radiative forcing is not just operating on the oceans, right? It's operating also on the surface. So if we're interested in the rate at which it's happening, we have to account for the land. So this is going to give us, let's see, 2 times 10 to the 15th watts. And remember, watts is joules per second. So it's the rate at which energy has to be transferred. So now we have joules per second, and we have joules, so how many seconds does it take? So we can say, okay, well, our time constant, which I'll call tau, is going to be equal to the amount of energy it takes, which is Q, divided by the rate at which it's being pumped in, R, and this gives us 17 years. So, I do want to comment that it's actually decently longer than this, because only a fraction of energy is absorbed by the mixed layer of the ocean, which is what we said. I might have said 200 meters was the ocean. This is the depth of the mixed layer of the ocean, which is what we're calculating. So longer. However, this gives us a time scale. This tells us that tens of years, maybe hundreds of years, is when we need to be concerned, which is now. So we really need to start paying attention to climate change and trying to deter our habits of dumping massive amounts of greenhouse gas into the atmosphere. Because if we don't, we're going to have huge, huge warming. And you know, you hear 2 degrees, 3 degrees, 4 degrees. It doesn't sound like much. It's going to have some pretty dramatic effects. So let me show you a very important chart, which is from the IPCC. I think that's where I got it from. So what I'm going to do is I'm going to graph the expected temperature change along with my error bars as a function of parts per million carbon concentration in the atmosphere. So let me try to draw this well. I should probably be using some kind of straight edge, but that's okay. Let's see. Alright, I think I did decently. So, this is going to be the equilibrium change in temperature above pre-industrial. So pre-dumping lots of stuff into the air. So this will be 2 Kelvin, 4, 6, 8, and 10. Yeah, this will be in Kelvin. And then down here, we're going to have greenhouse gas concentration in parts per million of CO2 equivalent, EQ. Equivalent means that, so I mentioned that water and also methane, for example, are also greenhouse gases and contribute to warming. So we're not just worried about CO2. So we want to know the greenhouse gas concentration in parts per million for all the greenhouse gases that are doing this type of thing, not just CO2. So if we hit, let's see, we're going to do 300 to 1,000. So 300, 400, 500, 600, 700, 800, 900, 1,000. All right. So the upper range of the chart that I'm going to try to draw here will look, let's see, so that's a rough, this should be a perfect curve like that. And so you're going to see 3 lines here. I'm going to tell you what they mean. And let's see. This one should be more like that. And our last one should look like. So, now this is the expected, but remember we have some uncertainty, right? Clouds are really difficult to model. So we're going to account for error. So it could be as high as this or as low as that. And I'm going to break this into categories. There's a few different scenarios. Call this 1, call this 2, call this 3, call this 4, call this 5, and call this 6. So, what do these mean? Well, we figured out about the time scale of how long this stuff's going to take. We know about how much we're increasing in parts per million every year, and now we can model the temperature versus this. So what this is situation 1, what's labeled as 1, is if we cap emissions and immediately and start decreasing the amount we're putting in after 2010. This graph is older. So we've already, 2013 is not that far. Same thing. Situation 6, you might think, oh, this is pretty bad. Up to 9 degrees increase? This must be far off in the future. Well, this is if we have business as usual until about 2050. And then maybe we start capping stuff. So as you can kind of see from this chart, we're not really in a great situation right now. This warming, this type of warming is going to cause, it's not going to be evenly distributed throughout the world. You're going to get more warming in high northern latitudes. You're going to get more very hot days, heat waves, fewer cold episodes, and you're going to have more precipitation. And when you do get that precipitation, it's going to be more intense also. Things we're uncertain about is the extent of the feedbacks. Clouds are hard to model, so we don't really know how that's going to impact things. And the latitudinal distribution. Ocean transport, the currents there, we're not sure how those are going to affect things. We're also going to have increasing growth in food production in the mid-latitudes, so that's cool. However, you're going to have desertification of dry and tropical regions. That is not cool. You're also going to have, people don't always think about this, but you're going to have an increased range for disease vectors. A lot of diseases are confined to certain regions based on temperature, but if you increase temperature in high northern latitudes where it's cold, diseases are going to start spreading more and more times of the year, and you're going to have diseases going places they haven't been more often. And you're going to have increased floods and extreme weather. Ocean levels will go up, floods will become common, more extreme weather, right? Hurricanes feed off of warm water, so that's going to be bad for us. So basically, we really need to do something. If you know someone who doesn't believe that this is real, I would encourage you to share this video with them because it's kind of hard to argue with science. And furthermore, take whatever action you can to try to, in some way, reverse what we have done, whether it be decreasing your carbon footprint or, looking at a larger scale and trying to work in policy to make policy changes or technology to find some way to take carbon out of the atmosphere or otherwise make our technology cleaner. It's really important. This is pretty much a huge disaster that humanity has brought on itself, and if we don't do something soon, we're going to be in trouble. So take this as kind of a call to action to do what you can to save the world. Thanks.